Good morning. How many steps was the mechanism for hydrolyzing an ester in acidic conditions? Don't feel like you have to guess. You've got this worksheet where I'm telling you exactly how many steps I expect it to be. 6 steps. How many steps to form an ester with an acid catalyst from a carboxylic acid and an alcohol? It's got to be 6 steps. If it takes 6 steps to tear it down, it must take 6 steps to build it up. So we are looking at the Fischer esterification mechanism. Instead of naming it after Fischer, what could we call it? Acid catalyzed. Acid base. It's got to be one of the two. When we did the hydrolysis mechanism, was that yesterday? We did a hydrolysis of a separate carboxylic acid and alcohol, so we ended up getting 2 different products. I don't know if you guys have seen this yet, but I like intramolecular reactions. They're quite useful and fun, but they can be challenging, so I want us to practice with an intramolecular reaction. So we'll be taking this 4-hydroxybutanoic acid, and we will be catalyzing the esterification, which is going to take the alcohol already on the ring and use it to make the esters. So we are doing an intramolecular cyclic ester formation. A cyclic ester, I might have said this earlier in the semester. Do you guys know what name is given to a cyclic ester? I don't like this name for IUPAC nomenclature reasons. They call a cyclic ester a lactone, which sounds like a ketone, doesn't it? A cyclic amide, where there's a nitrogen bonded to the carbonyl, a cyclic amide is called a lactam. So a lactone is our cyclic ester. What should we use for H+? Well, I don't want to use H3O+. H+ can be H3O+, because H3O+ is a source of H+. I don't want to use H3O+. Why not? And I mean this in context of a lab. I'm not going to get some sort of aqueous acid to use in the esterification. Why not? Aqueous conditions will hydrolyze the ester in reverse. So H3O+ is like the one wrong answer here. I want an organic acid. I want an acid that will be a proton source but won't be a source of water. My favorite option here is toslic acid. If you guys remember, toslic acid is actually para-toluene sulfonic acid. TSOH is great. Another option I gave you guys back with aldehydes and ketones was acetic acid. Acetic acid is not a great choice here either, because acetic acid is a carboxylic acid. It may end up going through the esterification instead of our butanoic acid. Or you could use H+, but the conjugate base of H+ is nothing. So it becomes really challenging to do these acid-base steps. Not hard, just something you have to actively think about. Where is my conjugate base? I have none. So I just show a bond to breaking, leaving behind H+. We start with protonation. How many things could I protonate? How many bases do you guys see in this structure? How many possible bases are there? You want to name them? Yeah, the oxygen of the alcohol, the oxygen of the carboxylic acid, the oxygen of the carbonyl, all possible bases. So when you approach this mechanism, how do you decide which oxygen should serve as the base? Do you remember where this oxygen comes from? The ester linkage. Jordan knows it.
Isn't it the alcohol on the end?
Good. The ester linkage oxygen is the alcohol oxygen. Forward and backwards all the time. You can always predict that this oxygen comes from the alcohol. So is it useful if I take this oxygen and use it as a base? If I protonate this oxygen and make it no longer nucleophilic? That is not useful because I need that oxygen to be a nucleophile. I need that oxygen to make a bond to carbon. So I'm not going to protonate that. Two other options. How can you rationalize whether to protonate the carboxylic acid oxygen or the carbonyl oxygen? Is it a gamble? Does it not matter? What are your thoughts? Do you know?
No, but I'm gonna say it's a carbonyl oxide.
Okay. Gut? Your gut's telling you that?
Well, if you protonate it, it's gonna make the carbon more positive, so that's gonna be more reactive. Plus, it's a pi bond. It's easier to break. It's just random
Great.
things like that.
We know that protonating the carbonyl oxygen makes the carbonyl a better electrophile. But we didn't say anything ever about protonating what's off of the carbonyl, making the carbonyl a better electrophile. So I want to protonate the carbonyl oxygen. There's another rationale that I gave you guys yesterday. Resonance. Yeah. The fact that protonating this oxygen allows for resonance between the two oxygen groups. But protonating the carboxyl oxygen doesn't allow for resonance at all. So I want to make my carbonyl more electrophilic, and I'm going to choose the base that has the most resonance in the conjugate acid. I hope I am making sense here when I say you've got three options and you need to be able to reason out which one is the right option. Or perhaps you memorize it. Or perhaps you say, I know that I will always protonate the carbonyl oxygen. If you are someone that struggles with mechanisms and you're going to bring a version of a mechanism, an example on your cheat sheet onto the final exam, make sure that you know how to interpret your mechanism. For instance, if you're given an esterification and you have a mechanism to copy, just recognize it's always the carbonyl oxygen. That just means having that vocabulary term in your pocket and knowing how to use the vocabulary to identify that stuff. Okay, here's something I've seen many times. A student gets to this step and then has tosylate, TSO minus, act as a nucleophile. Is that a good or bad idea? It's not a wrong idea. We look at O minus as a negatively charged nucleophile. It's not crazy to think that it should be the nucleophile to attack. Do I want tosylate to interact in here at all? Not at all. I want tosylate to be my conjugate base for my catalytic acid. This should only ever play a role of protonating, deprotonating. That is the entire job of this tosylic acid. Instead, what we said earlier, we know that that alcohol needs to serve as the nucleophile. So from our intramolecular reaction, we get this acyl addition. Because I'm in acidic conditions, nothing else is going to happen until I deprotonate my structure. And for that, we use the conjugate base, our tosylate. Now that I've reformed my catalyst, my catalytic acid, I should be thinking back in acidic conditions, what do I do now? Well, I need to protonate something. Once again, I have 3 options of things that I can protonate. 2 of them are identical options. Whether I protonate one of those OHs or the other does not make a difference. But whether I protonate this oxygen of the ether, what's going to become the ester, if I protonate that oxygen, I just undo the last step. So my options are clear. Protonate one of the OHs. We said that these acyl derivatization reactions, like hydrolysis of the derivatives to the carboxylic acid or formation of the derivatives from a carboxylic acid, we said these are substitution reactions. So if you show an addition step, you have to be able to follow that with an elimination step. For those of you that took my OChem 1 class, I always point out that elimination has what characteristic? An elimination reaction is always characterized by what change? What about a pi bond? Forming a pi bond. So in this step, I want to eliminate my good leaving group, which is this molecule of water that's bonded to my structure, but that would just form a carbocation. That doesn't form a pi bond. So where would the pi bond come from in this elimination step? Yeah. Either of those oxygens, to be fair, are able to share a lone pair and create a pi bond. The one that's most meaningful to us is when we form a pi bond from the OH group, because that is going to give us a carbonyl that we can deprotonate. There was a question I received on this once. In OChem 1 mechanisms, we often look at the mechanism for acid-catalyzed dehydration, protonate an alcohol, make it leave and form a carbocation intermediate. And this looks a lot like that. Protonate an alcohol and make it leave. Why would we avoid the carbocation intermediate? Why not show the carbocation here? Why not show the carbocation here? If we're going to do some sort of elimination later, why not just have a carbocation intermediate? If you can avoid a carbocation intermediate, you should avoid a carbocation intermediate, because carbocation intermediates have a lack of an octet at that carbon. So if there's an atom adjacent that can share a lone pair with that carbon, do it. Avoid that carbocation. we could actually say the same thing here. There's a resonance form of this protonated carbonyl, a resonance form where oxygen is neutral, and we have a carbocation. And this student's question was, if I saw a carbocation here, it would make a lot more sense to have a nucleophile attack. Okay, well, there is a carbocation there because there's resonance with the carbonyl. So when you look at that carbon, you should see a big old partial positive, bigger than a normal partial positive from just a CO bond because of that resonance. But that's not what the structure really looks like. That pi bond still has to break. And that's the struggle with Lewis structures that can exist and the MO theory that describes how all of the Lewis structures actually appear. So if this is challenging for you to understand why things happen the way they do, just think about what other resonance forms exist and how that can explain part of the mechanism. That is it for us on material to do. Oh, I forgot about this activity. I'll be honest, this activity has not this has not always gone the best. So I think I'm going to give you guys a lot of time for this. These new worksheets that I've handed out, once again, just an opportunity for you to apply the reactions, to understand the transformations and how they work. But the other activity that I want you guys to do is to try to create a synthetic pathway. And that might really look like taking the roadmap and just grabbing a chunk of it and saying, I'm going to do something like this. I'm going to do a conversion from a carboxylic acid and then into this and then into that. So the directions that I've listed out here is pick a functional group, react it with something, and make a new functional group. React that with something else, and make a new functional group. If you want to, you can take this a step further. And then the idea is hide some of this information. If you're going to go from A to C, don't give me 1, B, and 2. Those have to be solved for. How do I get from A to B except for, how do I go from A to C except for by going through B? Or go from A to D and take out all this information. Or what some people will do is give pieces of these. Essentially creating your own synthesis without necessarily saying how many steps. Like the problems that you guys get on your homeworks and on that midterm question. So here's what I want to do. At the top of the hour at 9 o'clock, I want to take those synthetic pathways from you guys and put them on the board so that you guys can practice solving them, but I'll also solve them. So I don't want to see your syntheses. I want you to come up with a synthesis. I'll solve them for you guys in front of the class. And you also will get a chance to solve it. But I want you to brainstorm. This doesn't need to be everybody makes their own. So how do you want me to do that? You want me to break you into groups for it? Or do you want to just kind of create groups of your own? I'll take like 2 to 3 of those syntheses and we'll solve them on the board at the top of the hour. Okay, so you have 35 minutes to work on filling in the roadmap and coming up with a synthesis. And I encourage collaboration. I encourage you guys to talk with each other, ask questions. Listen, if you feel like you're struggling with the material, this is the time to find someone who's not struggling and get them to teach you. And you're doing that person a favor because you learn a lot better by teaching other people. So collaborate. Okay, I'll be around to answer questions. Oh, and I'll put that roadmap on Canvas.
What if I want to do the
Yep,
Can I do that?
absolutely. If you want to do the homework, this is a great time for that. Okay. The carboxylic acid derivative roadmaps is on Canvas now.
Thank you.
Thank you. Hey.
It's the first
Retrosynth synthesis.
Yeah.
No.
Okay.
Because if you have a strong oxidizer, all of your alcohols will get oxidized. Close though. Okay, anybody else done with the front side? Just kidding, it's not fair, I made it.
Have you not done it yet?
I just made it yesterday. When was I supposed to do it?
Well, you just did it in 30 seconds. So. No problem.
Yeah, but I didn't remember all of them. I had to still figure them out. Listen, I will say, the difference between hydrazine in base and hydrazine in acid couldn't be different. And I would like to take a minute today, if I have time for it, to show why hydrazine in base and hydrazine in acid are different. We'll see if I am able to make that happen. And I don't think I messed up on the backside by showing any of the products. Oh, there was one reagent that I gave where you're filling in the structures. I gave an acid chloride. Oh, don't look at the answers though. Gave an acid chloride and I said limiting on the top right. That's not a way that I've ever shown it in class. I've never put a reagent up. You've seen that many times I've put a reagent up and put excess. But I've never put a reagent up and put limiting. So that's not something I commonly do. But if you get confused about it, I'll explain why later. I don't want to give it away yet. There is a reason why I said it the way I did. This is right. This reagent is this.
Yeah.
So the question is, how does
Yeah,
this
I don't know how that gets in there.
react? How does this react with this?
Is this formaldehyde?
It's not actually.
Oh, what's the difference between formaldehyde and this?
Formaldehyde has 2 hydrogens.
Oh,
This is nail polish remover, acetone. Okay, so I want you to think, what type of conditions are you in?
acidic?
I agree. So what's your base? It definitely could be. Any other options?
I don't know, I guess a carbon?
No, can't be a base.
So
Needs a lone pair or a pi bond.
yeah, the nitrogen, right?
The nitrogen can be a base, but is there anything else in the reagents that could be a base?
Oh, like within this? Because like the oxygen could be a base.
Yes, I agree. Both could be a base. And actually, we know that nitrogen is a better base.
Okay.
But if I have a nitrogen as my base, do I have any more nucleophile?
No. So it has to be this.
Right. Okay, so if I protonate this, we know that it actually becomes more electrophilic.
Right.
So now the question is, I have a good electrophile. What's my nucleophile?
The nitrogen.
I agree. So you are looking at a reaction between that nitrogen and that carbonyl at the top. Maybe I should have said this. This worksheet that I gave, the roadmaps, sprinkles in things from the entire unit. So it's not just carboxylic acids and derivatives, but also aldehydes and ketones. Just so you're aware of that. So that you can tell there's no carboxylic acid derivative.
Right.
So this is actually a reaction with the amine and
So this is the nucleophile then.
Mhm.
So it attacks the oxygen.
not the oxygen.
Is this acyl addition?
Yes, acyl addition, which is where you attack
The carbon?
the carbon. Actually, this is a common idea I see a lot. That oxygen is positive. Shouldn't it be attacked?
Oh, but the pi bond, like the pi bond electrons move.
Exactly. It actually already has the electrons it wants. It's just sharing them with carbon. So if carbon doesn't need to share anymore, that's going to improve it.
So then this would,
Good.
And that opens, and this whole thing would be like another bond coming off the carbon.
Mm-hmm. Now, you're using the mechanism to reason your way through it, which is good. But the usefulness of these sheets is that you can figure out what reagents you have and what reaction is going to proceed. That's just the tool that helps you be able to make that prediction faster.
Okay, yeah, that makes sense. Thank you.
Mm-hmm. So far, so good, Ju. Mm-hmm. Yeah. You're on the right track.
And then I'm lost from here. So I just add H3 and remove the N and just keep it an alkene.
An alkyne,
Alkyne. Does alkyne turn to
because there's no alkene.
Oh, I was thinking that like it would turn into an alkene.
Oh, I see, I see. How many carbons coming off of the ring?
2.
No.
Like 1, 2, 3.
Well, that one is a carbon in the ring. Do you agree?
Yeah. So
2 is the carbon off, and then 2 is triple bonded to the nitrogen. Or were you not convinced on that? Were you thinking that it was 2 carbons and then the external carbon is bonded to the nitrogen?
yes.
Because we can never assume hydrogens on nitrogens. So if you were to say, I think there's 2 carbons and then a nitrogen, what else is coming off of that nitrogen? Does it have 3 lone pairs? Because that gives it a 2- charge, which is pretty uncommon. Or does it have 2 hydrogens? But either way, because you had this, where did both of those carbons come from? There weren't 2 carbons in the step before, were there?
Yeah.
There's only 1 in the step before. So I think what you were meaning to write is this. It is a carbon to nitrogen triple bond, which we often abbreviate as CN. Maybe that will change it. But I will tell you, I have the roadmap, or the diagrams, that the reaction you're looking at is on this packet. So I trust you'll be able to find what product is made. You guys are okay with this mechanism if I take this down? It was not more challenging than the hydrolysis, was it? It's pretty much the same, just backwards. Tell me. That's good.
Did you already change the due dates, or are those just a week off still?
No, I did not change the due dates, actually. I need to change the pre-lab due date, but that's all I'm going to change.
Everything, like the lab project stuff is still due on the 30th.
Yeah. Yeah. No reason to... Oh, unless you... No, I think that makes sense. That's when it was going to be due. Jordan, I don't know if I told you, but my class is doing their final experiment. Oh, all 3 of you in Ty's class. Are you as well? No lab for you? Good for you. We're doing the final experiment next week while they do their second week of their project. The final experiment is short and easy. It's like mixing stuff together.
He does not like saying one.
He what? What?
I think Jordan can't be here next week or something, right?
Yeah.
Oh.
I have work next week, so I'm going for like the first half.
Oh.
But
But
we asked if we could run our second trial, if you will, of our own experience last night. We definitely would have had time to do it. But
really?
it's like, yeah,
Wait, which one did you run?
the winter grain oil.
Wow, and you had time to do it twice? How long did you cook it for? Really?
Purify.
Yeah, how'd you purify it?
Separatory final purification. And
Oh,
then dried it with the
Extraction.
extraction and then dried it on the hot plate.
Okay. Which is like, calling extraction a purification method, I don't know. It is, in a way, it's a workup. You are definitely pulling stuff out, but it's not a true purification. Do you know what? This actually makes sense. Last summer, I had students that did the same thing. They came in and they said, our purification is extraction. And I was like, no, it's not. That's not purification. And they're like, yep, that's what we wrote down. That's what we decided on. That's what we found in whatever procedures we're adapting from. I was like, okay, I don't like that at all. And they were gone so fast.
Yeah, ours was quick.
I should have maybe made them stay too.
But anyways, no, we wanted to stay and do the second one. He was like, no.
I don't blame him. If you guys can leave at 7:30, get the hell out of there. Or 8.
But then I would, cause
Why stick around?
like half of it alone next week.
Or will he? Maybe you guys will be so fast that you'll be done pretty much by the time you leave.
I have to leave by like 6:20.
So you have an hour to set up.
Reflexing the whole
Sure.
hour I'm there.
Sure. No, you'll have to prepare too, so at least you can do some of the heavy lifting with preparing it.
Yeah.
How would you purify it then?
Different options exist. A lot of the procedures that report on wintergreen say that you should purify it by vacuum distillation.
But then he said that
I didn't
doesn't
want to
work
do that one.
either.
I didn't know.
So vacuum
He said that
vacuum distillation is
you
like,
can't get it hot enough or whatever.
correct. Alec, well, I'm not sure that you guys remember Alec. Alec didn't come to lecture very much, but Alec actually ran the lab ahead of time. So Alec did wintergreen oil synthesis, and he actually did it 3 times because he had the chance to and he wanted to. And he tried vacuum distillation the first week, but it just wasn't successful enough. He got his layers mixed up. So he tried vacuum distillation the second week, and he was cooking it as hot as he could get it. He had it wrapped in foil. He melted the little like plastic spacer that goes on top of the red cap, melted it completely. So it's not even that our heating mantles can't get hot, but it is really challenging to distill, especially with our stuff. And Ty, I don't think is having you guys do everything in the fume hood, but I'm having my students do all of the experiments completely in the fume hoods. And that actually wicks away a lot of heat because of the air coming past it. So it's even harder to get it hot enough to vacuum distill it. But I think it is possible. And I'm never going to tell a student no if that's the method that they came up with. Is that the method you came up with? Anyways, so yes, I've seen people that say like, I'll just do extraction and drying to make it pure. Yeah, it probably does make it pure, to be honest. That's how we purified 1-bromobutane back in the OCHEM 1 labs. We just do extractions. But distillation is the most common method for purifying a liquid. Like with banana oil, we distilled it. But then with DEET, we didn't distill it. With DEET, we passed it through column chromatography, and anything that was more polar than it or byproduct got stuck in there. So you might be able to do column on wintergreen oil because the wintergreen oil should be less polar than the salicylic acid starting material. You replace an OH with an OCH3, so it decreases polarity. It means it should be easier to push through column. But I've never seen any procedures report on using column chromatography to purify wintergreen oil. So I guess you picked the right idea by just doing extraction. It's the easier way to go. It's not really purifying it.
I think our IR was pretty close.
Oh yeah? You know, it's so funny. Even if you make a tiny little bit of wintergreen oil, which happens very often. I see students that just make just a tiny little bit of it. It's everywhere. You smell it on every piece of glassware. You smell it in every layer. You like smell your aqueous layer and you're like, yeah, there's wintergreen oil in there. You smell your organic layer, yeah, there's wintergreen oil in there. But you can't get it. I've had students that just can't get oil. They keep getting this like sludge, which means mostly the salicylic starting material crystallized and just like was wet with oil. But then I've heard of groups that get really good products. What was your yield?
I didn't write it yet, but
Didn't calculate it.
Probably not good because someone spilt it.
Oh. I forgot to close the
The stopcock, yeah.
Yeah. So probably not very good at all.
Rookie mistake.
But
Literally.
like our product was like milky white, and we had like really low liquid, and then
But yeah, the other groups was like actual oil.
Clear oil.
It was a yellowy.
Oh,
they used
yeah, okay.
vinyl something.
They used what?
They used
Thionyl chloride?
instead of
Oh.
using, what did we use?
Oh,
just
we
used,
won't talk about that.
Sodium bicarbonate
And sodium chloride.
yeah.
Good. But you didn't use an organic solvent,
Yeah.
like diethyl ether.
We
Yeah, we
did.
did.
Oh, okay. Yeah. So dichloromethane, methylene chloride, is one of the greatest organic solvents of all times. It is incredible at doing its job. It's more dense than water, which sometimes is a benefit in separations. Sometimes it's not a benefit. It's really it's really good at dissolving pretty much everything organic, a lot like acetone. But it was a suspected carcinogen for a long time, and the EPA recently regulated it, like within the last 2 years. So now it's a known carcinogen, and to use it, you have to use it with certain criteria, regulations. Like your fume hoods have to be pulling a certain amount. You can't leave your fume hoods, even if you're rotovapping it down, which is, we don't do that in our labs, but you spin it in a water bath and get it and pull vacuum, so you like evaporate off the solvent quickly. Even all of that has to be done inside of a fume hood so that none of the DCM escapes. So we don't use DCM anymore. A lot of our procedures had DCM like every single week. And part of my job in rewriting the curriculum was just find and replace DCM with diethyl ether, which is sad, but I need to throw out the DCM that we still have. It just sits there.
Is that why in the procedures in the textbook it says the organic layer's on the bottom?
Yep.
Instead of top, 'cause it's more dense?
Yep. That's why. If you're using DCM, it'll sit below the aqueous layer. Not very common that an organic solvent is more dense than water. Okay, in about 10 minutes, I want to take those synthetic pathways from you guys. So now might be a good time to kind of sit by each other and decide how many steps do you want to do and what do you want those steps to be. Honestly, if you want me to leave so I don't hear anything that you come up with, just you tell me. Otherwise, I'll just sit up here and draw a mechanism.
John, will you look at
Yeah? Look at your what?
this, right?
Okay, I don't know if you translate me and I guess that's
Well, it's not H2O2. I did make that mistake. I asked you guys
This
to.
is from, oh, maybe
No. Oh, yeah.
this is from this.
I think.
I just was on a different one.
This reduces something.
It's H2.
I think it just gets rid of the
Yeah.
On all of them?
Yeah, it's H2SO4,
On, or just the ones with chromic acid?
like normal. Yeah, so you know how I made that mistake? I just copy and pasted ozone. It was supposed to be chromium trioxide and sulfuric acid.
Yes.
Okay, this is
no,
This is good to know. I think I'm going to have to go generous if people don't put sulfuric acid.
That'd be really nice.
I mean, that is quite literally my fault, right? So, what can I
And I
say?
wasn't even here in class.
Right, exactly. Great. Yeah, that's exactly it.
Oh,
Great job.
Yeah, so maybe it makes a.
He also says don't change too much, because otherwise if it does fail immensely,
Oh, no, I can
like
come
people
sorry.
are not gonna know exactly what went wrong. So that's why I'm like, okay, if we changed the amounts, for sure.
Okay, anyways, let's make our,
I've been doing.
Hi, Brenna. So, Brenna, we just spent the last hour, we went over the acid catalyzed esterification mechanism. We did the hydrolysis of that yesterday, so just the reverse. And then they spent like half an hour going over the new roadmap. I have a roadmap worksheet. And what they're doing right now is creating a synthesis. So if you want to join a group and just see what thoughts they've already had and see if you have any to contribute,
What should we try and make?
I'm going to solve them for you guys.
What if we do an internal analysis and into something,
We have to choose one. We said alkyne can be our functional group starting with two. And we have to choose a new functional group we need for. So either not or carboxylic acid.
what would you do that time?
Those are the only thing we know how to do that. Like,
Maybe we should just put reagents and then just figure out the. And it could be anything.
wait, what are we supposed to remove? Oh, two start to just try and use it.
I'll just put in a bunch of random reagents.
Okay, so it has to be really cool.
Honestly, yeah, it does. So, oh wait.
Yeah, that'd be.
Okay, so let's take something to start with.
Did you say you wanted to start with acid? We can.
Or we could do like there's those
I guess we can try and use like the biggest RBF we have. Try that.
That's weird. I don't like that.
Well, I guess if we wrap it,
But I think we're supposed to
a big difference.
choose a functional group starting with two. Oh, but also does sperm either 14 can be functional group. So we start with the functional group. Choose your reactions from this and then make the second one.
Yeah.
And then keep. Okay, let's do this. Do this pull up. So then with the
Did I fix the synthesis question? I'm tired, so I don't know if I did it or not.
Yes.
Okay.
Yes. That's exactly right.
and then we work that with. Wait, how many things are we supposed to have on together?
What? I erased it. You could go from like a two-step. So you're going to have a missing intermediate and two missing reagents. Or you could do three-step. And so you're going to have two missing intermediates, three missing reagents.
So all we give you is the beginning and starting?
Beginning material and product. Yes.
Oh.
Yes, beginning and starting, I think, are the same thing.
Oh, sorry.
Right? I do that. How often do I do that? Every day.
And then from there.
You said it's going to be boring? Oh, well, now that you've had some practice, try again.
Because we get to go here, and then, what if we do? No, that's such a good idea. I've never thought of that one before.
Try me.
Doing stuff for funsies. Just showing off.
I'm practicing.
He's showing off.
He has a midterm tomorrow.
No, I'm demonstrating why acidic and basic conditions with hydrazine have such different effects. So both of these reactions take acetone and hydrazine. But one of them takes acetone with hydrazine in basic conditions. One of them takes acetone with hydrazine in acidic conditions. And you can see they actually share a structure. The final product, hydrazone, in acidic conditions, is also formed in the Wolff-Kishner reduction. You guys remember the hydrazine reduction? Taking a carbonyl and making it an alkane by way of hydrazine in base, which is different than taking a carbonyl and making a hydrazone by way of hydrazine in acid. I've never actually done this mechanism, so there could be a problem with it, but I'm not seeing it. I see things I'm uncomfortable with, but I don't think it's wrong.
Is the OH a good enough leaving group?
It's very strange to have hydroxide be a leaving group, but we are going to see that in Unit 5. We're going to see hydroxide be a leaving group. I'm not excited to be done with the semester too early. You know, next week is our last week together. And then the week after I'll be gone. And then the week after is prep for the final.
What are you doing in that week when you're gone? Have you decided, at least for lecture?
Some
I originally was going to ask someone to come in and sub, but that person said, I like to come in every day at 9:30 at the earliest. And I was like, oh, that's the end of class. So they're not really looking forward to subbing. So, and to be honest, the sub was going to run a flipped classroom, meaning I was going to tell you guys to go watch past lecture videos and then just come in to get answers. I'm not sure that this sub I was going to choose would have, like, no, they could have answered questions. I just don't know if that's their forte, you know? They would have gone on these different tangents. They would have brought you to be an organic chemist rather than an organic chemistry student. So I don't like the idea of just saying have a week online when it's the week that you could be using to ask questions and stuff. honestly, what I might do is just try and get you guys to go meet with Johnny Pope, the tutor at the tutoring center, to basically run a flipped classroom from his perspective. He took my OChem too, so he'd be able to do it. Yeah, I'll update you guys next week.
So is next week gonna be the last week of the new material?
Mm-hmm. Well, yes and no. So you guys have seen that I can just hand you a document, and now you have all the reactions. And I can show you the mechanism, and now you have all the information you need. And after that, it's just learn how to apply it, learn how to run it. So there might not be much that I have to, I don't think I'll be missing much that week that I'm gone. I'm not gonna miss a lot of delivering class material, just missing the time spent covering stuff, or answering questions, doing this. Are you guys ready to give me some of your syntheses? Here's what I'm gonna do. I'm gonna,
Wait, what did you say you were end up doing, just online class? Or will you just make a full, like, just tell us which videos to watch? 'Cause
Mhm.
I probably won't.
yeah, absolutely. I'm not gonna ask you guys to go find videos that you think might be useful. I'm gonna send you videos. And I'm gonna talk with Johnny to see if he would be open to basically running like a review session every day with you guys. I have heard students say that Unit 5 is not the most straightforward unit. So it's not something that I feel comfortable abandoning you guys on and then just saying, show me how your final goes. You definitely need the support. And the lecture videos are support, but they're not the same as getting answers from people. All right, I'm gonna start with justices since it's the most diabolical. How do I take one equivalence of acetic acid and get two equivalences of acetic acid? Okay, I feel like you had more information on your sheet, so I saw an idea of what your pathway was. But my thought process here is I'm going to end up hydrolyzing something that has two equivalences of the carboxylic acid. And you know what has two equivalences of acetic acid that forms two equivalences by hydrolysis is acetic anhydride. It's the only one that will hydrolyze into two equivalences of acetic acid. So now I need to see how do I make acetic anhydride from acetic acid. And I think you guys had a different route, but there's one step here. Take a dehydrating reagent. Oh, no, you know what? This doesn't work because that just takes my sample, splits it in half, and then gets it back. So you're right. This isn't the route that you wanted. I know because I saw that on your sheet. So turn this into an acid halide. And then introduce a carboxylate acetate. That's where the second equivalence comes from. And then I make acetic anhydride, hydrolyze it into two equivalences. Good synthesis? Okay. I won't give that to you. I feel like that's a little wild. Okay, I want to do this one next. So in mapping my carbons, I'm noticing that this phenyl group is new, but everything else was already there. So I need to add a carbon-carbon bond, organometallics, that's what I'm thinking. It wouldn't have to be organometallics. Okay, there's two routes, two synthetic routes that I see here. One would be using an organometallic to do acyl addition and leave me with a secondary alcohol. Do you know what forms a secondary alcohol by way of acyl addition? Aldehydes. Aldehydes give me a secondary alcohol by way of acyl addition. So now I need to figure out how to get an aldehyde from my carboxylic acid. That's not a full reduction. So if I use something like LAH, it would completely reduce all the way down to a primary alcohol. I want to do a one-step reduction or a partial reduction. So I'm going to use Dibol. Partially reduce the carboxylic acid to an aldehyde, and then acyl addition with a Grignard. Was that the route that you had seen? Okay, here's another route. Another way to solve this. This would be more steps. So actually this is the shortest route, which is good. This would be more steps, but I can bond carbon 1, my carbonyl carbon, to the aromatic ring by acylation if carbon 1 is an acid halide. So what I'm going to do is convert this into an acid halide with thionyl chloride. And then I'm going to run it with benzene and my catalyst, aluminum trichloride. And this allows me to create my ketone. And then a ketone is related to a secondary alcohol by means of reduction. So LAH or sodium borohydride would reduce my aryl ketone down to the secondary alcohol. That's 3 steps instead of 2. So what you guys had done was the most efficient synthesis instead of my 3 steps. Okay, this is a good reminder that even when I come up with a synthesis problem to give to you, it doesn't mean that there's only one route. Maybe there's one best route, sure. Maybe there's one shortest route, sometimes that happens. But a lot of times there is more than one useful route that uses all of the same reagents that we've seen all semester long. All right, now for the last one. Okay, I don't think that I have to build every part of that structure. You know, this is another thing about synthesis that I don't lean into quite as much as other instructors that I've seen. A lot of instructors that give synthesis problems will give limitations like complete the following synthesis using reagents that have 6 carbons or less and any inorganic reagents that you want, which means that you get some freedom about creativity. What do you want to invent almost? Maybe if you've never seen it, it might feel like you're inventing it. What do you want to dream up to use in your synthesis? I don't even give you guys those limitations to try and hopefully let you imagine for yourselves what all could go into the synthesis. But here, I'm not going to synthesize every part of that molecule. I'm going to introduce parts of them as reagents. So in mapping my carbons, this is what I see. I see an alkyne that can be split into 2 equivalences of propionic acid. And so I'm going to split that alkyne, and I'm just going to use the 2 equivalences of propionic acid as one reagent, propionic acid. To cleave my alkyne, I need to do some hot oxidative cleavage with potassium permanganate or oxidative ozonolysis. Split that into 2 equivalences of propionic acid. Now, I see an anhydride, and I only have 2 ways of making an anhydride. I can make an anhydride by P2O5, dehydrating 2 carboxylic acids, like what I did over here. Although that didn't give me twice as much of my reagent in that last one. I don't think I want to use P2O5 because I don't want a symmetric anhydride. I'm looking for an asymmetric anhydride. So I need to make my carboxylic acid into an acid halide, thionyl chloride. And once I've created my highly reactive acid halide, I introduce it with a carboxylate that can substitute the chloride. So in this case, the carboxylate is NN-dimethyl, I don't know the name of it. It wouldn't be formate, formamide 8. I don't know. Anyways, it's going to have this nitrogen group on it already, and it'll have a carboxylate on the other side. So this is a type of like form group. Remember we had formaldehyde. We can also have formic acid. We can also have formamide. So this is just a version of that one carbon carbonyl that is both a carboxylic acid and an amide. It does happen quite a bit. You guys know urea? We used to have a reaction that used urea in the OChem labs. Urea is like a formaldehyde derivative as well. It's a formdiamide. You've used it?
I've seen the reaction in OChem 1.
With urea?
Yeah, when we talk about it, it's turning, I can't even remember.
Oh, there's a lot it can do. There's not just one thing.
Like the very first reaction or whatever. My Dr. Chamberlain likes to talk about how OChem
Oh, was,
urea.
yeah, okay. The first ever synthesis of urea from inorganic reagents. It used it used nitrogen and carbon dioxide and some, I don't know what else, hydrochloric acid. Yeah, you're right. That was like the birth of organic chemistry. It used to believe that organic molecules had something in them that made them vital. They had some vitality to them, vitamins. And so people believed that organic molecules could only be made by organic things. People used to believe that inorganic things could not create organic things. So the synthesis of urea was first reported. Okay, how'd I do? Was that your idea? Yeah. If it's not, don't tell me what I did wrong, but tell me if it.
I think that makes sense.
So you had a different route.
No, I didn't have a route.
Oh, you didn't solve it? You just drew the starting material and product. Okay, well done. That makes sense. So you guys are okay with the fact that I didn't make this reagent from your starting material. I just introduced it because it didn't make sense to make it. If I were to try and make it, I'd have to cleave a bunch of carbons, and that's going to be hard to do. So, okay. What'd you learn from that? On paper, you should have seen me in the first week of lab. I told my class, I want you guys to try a synthesis for me where we basically rerun all these reactions that are so common in OChem 1. So show me a substitution with hydroxide, and then show me a substitution with alcohol, and make an ether. On paper, that's what I teach all the time. And in practice, nothing happened. Nothing. The hydroxide and the 1-bromobutane,
By himself too during our labs.
it did nothing.
Heating it up.
And that's true. I put it on a hot plate to like 50, but today I want to try it again and I want to reflux it. I kept asking AI too, how do I improve the synthesis? And I kept like putting limitations on it. No, I don't want to do this. I don't want to do that. I want to make it useful for my students in lab. And every single version that AI pumped out said you need a phase buffer, something that helps get the organic and the aqueous to actually mix. And it was some like tetraethyl ammonium chloride, which is both ionic to mix with water, but has these alkyl groups to mix with organic. And we don't have that. So I'm going to try it again today. I'm going to reflux it. I don't know if it's going to work or not. Okay, what I hope you learned was that even the one that gets paid to be here, can find more than one route sometimes. So if you find more than one route, that's great. But I hope I demonstrated mapping my carbons so that you can visualize how certain groups are going through specific changes. I noticed that it was Esmeralda and Jaylee's carbonyl carbon that bonded to the aromatic ring. So I'm paying attention to what carbons are bonding where. That Jew's carbon got cut in half to give me two equivalences of this. Try to be creative when you're doing a synthesis. I know that synthesis is one of the most challenging things. And I know that on the final, solving the synthesis is like 5 points out of 100. And so it can look really tempting to just leave it blank. I get students that leave the synthesis blank all the time. I also get students that leave the entire mechanism page blank all the time, every semester. I fully anticipate this semester there will be at least one exam that just leaves it blank. Try. You cannot score lower than if you don't put something. Putting nothing gives you a 0. Putting something means that there's the chance you get some partial credit. So put something. We've got 10 minutes left. So questions that you have on the worksheet, I'm going to upload the worksheet, the answer key. Okay, right, so I've got that reaction with the acid halide. I guess what I'll have to do right now, though, is I'll have to give it away that you've got some amine and then this acid halide. And what I've said underneath it is that this is limiting. What's another way of describing these reagents and saying that this is the limiting reagent? I can say that the amine is in excess. And that's what I've given you guys before, is that an acid halide with an amine reacts in excess. But because I couldn't tell you that it was an amine before, I didn't want to put excess here, so I just said limiting. Was that the clarification you wanted?
I think that makes more sense.
Great. So saying that this is limiting is exactly the same as saying that the amine is excess. Okay, the rest of the time is yours. I'm happy to answer questions, look at your homework, whatever you need. We've got a unit test this weekend. Yeah, I need to grade homework today or tomorrow for sure.
That's okay, because I'm behind, so.
So at the beginning of the semester, the assignment for the hydraulic spectra, I had like forgotten to include a functional group, and then you just told me to like add it and I submit it, and I did.
Oh, and I never saw it again. And I think that's because of the discussion boards that I'm using. The discussion boards don't always tell me if there's a resubmission to regrade. Could you do me a favor and comment on it?
On the assignment?
Yeah.
Discussion.
On the assignment. Yeah. I don't know. Can you do that? Like from your grade book, see the you know what? I'll try to do it right now. Well, I want to keep the recording going in case I answer any more good questions.
I can't comment.
The thing is, if you comment, it gets sent to my email, and that will give me a way to open it and grade it. Thank you. Mm-hmm.
I did the first one.
For the mechanism. Forgot your positive charge on hydronium. Forgot your positive charge on hydronium. Forgot your positive charge on that protonated ether. Otherwise perfect. Your arrows are perfect. You're just missing your charges.
Oh, it's oil.
Right. Sorry. I was like,
What the heck?
you think that's pure? But that's actually not a carboxylic acid stretch. That's your alcohol stretch. Great job. I forgot that salicylic acid or wintergreen oil has an alcohol.
The thing was our ester was a little lower because it was supposed to be 1700.
1700 is the middle, but it should go from like 1775 to 1715.
Yeah.
Oh, yes.
So why is it all the way down at 1672? Actually, do you know what it tells you when a CO double bond absorbs a lower frequency?
Probably have a higher elevation.
Is it because
No.
of conjugation?
Yes. The weaker the CO double bond, the less energy it needs to vibrate. So why would this CO double bond be weaker than this CO double bond? Sorry, why would this CO double bond be weaker than this? Why would this absorb higher frequency because it's stronger, but this absorb lower frequency because it's weaker? Or another way of saying weaker, less double bond character. I know you look at this and you say it's got double bond character, but I look at these and say they have less double bond character than this. This has more double bond character. The reason I say that is because of resonance. This double bond is actually only a double bond some of the time. It shares double bond character with the other oxygen, so it's not really a double bond, it's like a 1.75 bond. Here, there's the same amount of resonance from that oxygen, but there's also that electron withdrawing effect from the ring, or of the ring. So that adds another piece of resonance that lowers the double bond character, lowers the frequency it absorbs. Conjugation. And then you know what absorbs at the lowest frequency of the carbonyl family? The CO double bond of the amide absorbs from like 1695 to 1615 or something. Why does this absorb at such a lower frequency? Because this resonance is so much more significant. Because nitrogen is a much better sharer of electrons than oxygen. And so the double bond is weaker more often. What absorbs at the highest frequency? The acid chlorides and the amides. Because there really is a lot less resonance to the carbonyl, so the double bond character is more prominent. Higher frequency. Isn't that cool?
It's very interesting.
So yeah, it is. And if you look at SDBS, I guarantee you'll find the CO double bond is
A little bit lower.
right around there.
Oh, so we did it right.
Mm-hmm.
So when we're trying to improve it, I mean, like, obviously we're gonna improve it because I spilled some. But
Sure.
Drew, I'm just kidding. I hope you know that.
but we're
How are you going to write that into your procedures to improve it?
Jew, spill.
we're thinking about refluxing it longer, like 10 minutes longer.
Yeah, have you heard about the law of diminishing returns? It says that the longer you run something, the less you're actually going to get out of it. So if this is your 60-minute mark and you're getting maybe like 60%, you run it for another 10 minutes and you might get 65%. So 10 minutes could be useful, but honestly, if you're going to change the time frame, I'd say run it for a day. You don't have that option. So 10 minutes, yeah, it's not going to hurt, but I don't think it's going to give you that much more of a impactful result.
What could we change? Because we used 2 grams and then like methanol. And,
Yeah.
which was
How much sulfuric acid did you use?
1 ml.
Yeah, I'd start there. The procedures that you were basing it off of, did they recommend 1 milliliter? Do you know? Yeah, so you just took the...
We used only 10 ml of methanol.
whatever masses and volumes they gave, is that just what you used?
Yeah.
So you didn't put any thought into why do I want to use 2 grams and 10 mils and 1 mil?
I think the salicylic acid was the limiting one. So
Mm-hmm.
it doesn't matter if we use like 1.5 to maybe if we use like 10, that's a lot. But
I agree. So actually, methanol is your excess reagent. Methanol serves another role as well, though. Serves a role as your solvent. So methanol is both your solvent and your excess reagent. You're running a solvolysis reaction. So if you look at the stoichiometric excess, your methanol, 10 mils of methanol to 2 grams of salicylic acid, is like a 500-fold excess. Because it doesn't matter how much excess it is. The more excess, the better. Actually, just the more solvent you have, the better. Sulfuric acid is a catalyst. So how much of it do you need to run the reaction? 1 molecule, in theory, right? 1 molecule could go around and catalyze every single reaction between every molecule. It would just take a long time. So the more catalysts you have, the more likelihood you have of having things protonated when you need them protonated. So there are some procedures out there that report 10 mils of sulfuric acid. And I've seen a lot of students that cut back on that to try and make it seem more like a catalyst. But I would say you could double your amount of solvent and your amount of catalyst, and that wouldn't be a bad thing at all.
what happens if we just double the catalyst only?
Yeah.
Like triple it.
And I would say whatever modifications you make, keep them targeted, keep them small. Don't make a bunch of changes, because if things improve or get worse, you don't know what change did what.
Yeah, also when we were drying it on the hot plate in the fume hood, it was like cold. So Tyson
Yeah.
would do a warm bath and then dry it.
Actually, the reason that your beaker gets cold when you're evaporating is because to get that solvent out, it has to take in energy. And where is it taking energy from? The glass. And so it's your evaporating solvent is taking more energy from the glass than the glass is taking from the hot plate. That's why it gets cold. Yeah. That happened in the caffeine lab. Oh, we don't do the caffeine lab anymore. But anytime I have students evaporating solvent on a hot plate, I have them go in and touch it and feel that it's cold to the touch, despite the fact that they're boiling off a solvent. Thermodynamics.
Does that warm bath help with?
Maybe, but I would say if your solvent was evaporating, doesn't matter whether the glass was cold or hot. I don't think a hot bath is going to be that much more helpful for getting the solvent out. Was it hard to get rid of the solvent?
No, it was like going away really fast.
Yeah, then a hot bath isn't going to do anything. The only reason it's cold is because it's working.
For the benzocaine lab, our melting point is low.
How low?
Like, it's like 90 to 92, I think is the literature one. Ours is like 80
Mm.
to 81. No, it was like 1.5 to 86.
Okay, so it was kind of broad and low.
Yeah.
So that would be a purity thing.
So do you think maybe we didn't dry it enough?
Yeah, actually drying the benzocaine is something that I've heard people have they struggle with a lot. That it's hard to dry benzocaine. We had 2 students that went on to develop their own research project around synthesizing benzocaine after going through the OCHEM 2 lab. And they would take their product and they'd put it in the oven to dry at like 70 degrees.
Okay, because Ty mentioned that.
They would do it for like a day or 2 or more because they were doing it as a research project.
But wouldn't it melt?
If you put it in an oven above its melting point, yes. But if you put it in an oven below its melting point,
So we did like 60,
mhm,
it would dry pretty well?
it could help evaporate off some of that solvent.
What if you leave it at room temperature? Will that dry it?
It depends on how long you have. Yeah,
A week?
yeah. You leave it for a week. That would help dry it well enough, at room temp even. There's something to be said though that if you are evaporating off a solvent quickly, that can cause the molecules of solvent to break past your crystalline structure and ruin the purity that way.
Yeah, because when we were cooling it to room temp, no crystals formed, and then once we started mixing, like crystals formed.
Mm.
But if we stopped mixing, then no crystals would form. So we had to keep mixing.
To get the crystals out.
Yeah.
And you used two different solvents. You had water and ethanol in your recrystallization.
Yeah.
And you followed the procedure to where it says add enough hot ethanol to get it to dissolve, add enough hot water to get it to crystallize, and then replace it with a little bit more hot ethanol to get it to dissolve.
Yeah.
So you felt pretty good that you used the least amount of both necessary.
I think we maybe might have used, because we used methanol, but I think we might have maybe used too much methanol to begin with to dissolve it.
Okay, that would be a problem. That would be part of why you didn't get crystals back.
Okay.
I also would have had you put it right in the ice bath and not stir it. So if it doesn't crystallize at room temp, put it in the ice bath and see if it crystallizes there.
Okay. And then if it doesn't, we can try to scrape the sides.
Yeah.
Okay.
Or like put a glass stir rod at the bottom and go. If it doesn't give you that nails on the chalkboard feeling, you're not scratching it right.
Okay. Okay. That helps. Thank you.
You bet.
How do you do this?
Good luck on your unit test this weekend.
Could you do that, or is
Which
that
one?
not allowed? Maybe get an alcohol
Um,
first?
A Grignard and an alcohol is just acid-base chemistry. Yeah. You want to add 1 carbon, so you've got a 1 carbon reagent, which is great, but you want a 1 carbon carboxylic acid.
Well, how do you do that?
Yeah, good question. How do you make a 1 carbon carboxylic acid?
If we create a vacuum or not.
Thank you.
See you, Brenna.
I don't see
It's on there.
one carbon carboxylic.
Or sorry,
With it,
it adds, it makes a carboxylic acid by adding 1 carbon.
correct, okay.
That's on there.
But can you do them both in one step? That's where
Yeah.
I'm confused, because
Mhm.
when we have this with organometallics, we have like an ester, but we don't have,
Yeah, we don't have a carboxylic acid,
yeah.
right? Because also those don't produce carboxylic acids. We want a
This
reaction
does?
that produces. All of these produce a
Right,
carboxylic
oh,
acid.
this is what we need, okay.
1 carbon, organometallic,
Oh.
makes a carboxylic acid. Add some CO2, and you're good to go. Justice, you got a question?
On the written homework, the second synthesis,
Uh-huh.
like what the heck? Really? Like what do you, can you like point me in the right direction for this? Cause like, I was gonna reduce with LAH, but then that would get rid of that.
Okay. It would get rid of that and make it what?
Primary alcohol.
Okay.
And then, like, what do you do from there? Like, do you want the carbonyl there?
Well, do you?
Well,
I would
feel
map
like-
your carbons. That's what I would do.
I feel like you do, cause it's right there.
Sean, see you next week.
See you next week, Jordan.
1, 2, 3, 1, 2, 3.
Okay. So the carbonyl we have, we want to keep.